My name is Hayk, and I work at BiosimAI, where we build tools for computational drug discovery. So I will be talking about BiosimMD, which is one of the things we've built. It's a fast and versatile molecular dynamics library, completely written in Julia. A brief overview of drug discovery. As a first approximation, drug discovery problem takes in a protein target, and the goal is to find a compound that will bind to that protein target and inhibit, for example, some of its functionality that's causing a disease. Typically, you start from a large database of compounds, billions of them, and through stages of filtering, you get to just a handful that will go to clinical trials. So my colleague here actually talked about some of the earlier stages of this a couple of days ago in the talk called BiosimDoc. But we'll be talking about the later stages when you have only a few compounds you want to test, and you can afford to spend large computational resources and do molecular dynamics on it. What is molecular dynamics in this context? So it uses classical force fields to simulate the movement of particles to predict protein ligand binding. In this case, you can see a ligand that's in a pocket of a protein, and we're simulating the process and their interaction as time goes on. So this is a very heavy task computationally because basically every step of this process, we are simulating 10 to the minus 15 seconds of real life time. And nothing interesting happens in that time scales in biology, only some hydrogen atoms vibrate. So to get to interesting processes, you need to do billions of these steps. And bear in mind that at each step you compute pairwise interactions between atoms, and there's tens of thousands of these atoms. So we don't want to leave any performance on the table. So how does BiosimMD's ecosystem work? At the core of BiosimMD's ecosystem is a package MD engine, which contains the core molecular dynamics algorithms. And it relies on a few internal packages we've developed. One of these is, for example, BiosimSimD, which extends the SimD package you may be familiar with. And then we have implemented BiosimThreads, which is a thread pool type of package to manage multi-threading simulations, where we get very good speed ups on multi-core CPUs. We've also implemented the package MDStructure, for example, for allowing us to easily manipulate and iterate over molecular structures. So that's the core of the MD we have, but then there is also application layer where interesting and complicated sometimes computational algorithms, computational chemistry algorithms are implemented. And many of these algorithms, they actually don't run one very long simulations. Instead, you actually need to run shorter simulations, but all of them in parallel. These needs to be coordinated, and they exchange information as they move in that simulation. So to facilitate all this process and this application layer, we've also implemented a package called ParallelMD, which uses distributed JL underneath to spin individual molecular dynamics processes, coordinate them, and so on. So the application layer uses this package underneath. What does this all look like in practice? I've implemented the interface showing here in Jupyter Notebook. So of course we load our package, and then we load a system. In this case, we can load from PDB bank a protein using its code and visualize it directly in the notebook. Then with a few lines of code, we import this system into Biosim's data structures that allow for fast molecular dynamics. What we'll here do is actually select the ligand and the pocket surrounding it, and also visualize it. The ligand here is shown in red, and the pocket around it is shown in yellow. Next we create a simulation out of this object. We set some logging parameters with a few lines of code, and I'd like to bring your attention to this, which allows us to customize, for example, the simulation. We add a spring, in this case, between a ligand and the pocket, and the spring gradually increases in length as we move. So that will push out the ligand out of the way out of the pocket during the simulation. It's just a few lines of customizable code. Then we initialize our simulation and run it, in this case, for just 1,000 steps, because I've run it before in this notebook already for 150,000 steps. We wait for it to finish. The 1,000 steps will be done quite quickly. So now that it's done, we can do quick analysis of the trajectories in logs it generated. So here on the left side, actually we plot the distance of the ligand and the pocket that we saw earlier over time, and we can see the distance increases as the time goes on, which was kind of expected. On the right side, we see the potential energy of this spring during the time. So we see that the potential energy is actually increasing, and then at some point this spring relaxes because the ligand managed to move out of its pocket. So these are the type of things we can visualize and look at in our analysis process. We can also look at different frames of the simulation. Here I visualize the starting frame that you've already seen and the last frame, where we see in blue that the ligand has actually moved out of that pocket, as kind of expected from the plots and the simulation we've set up earlier. So this is a notebook that you'll be able to access in our partners platform. It's called, the platform is called Deep Origin. So what about performance? I'm reporting here a performance on a system of about 100,000 atoms, where we compare BiosimMD, in this case, on a single CPU core to GROMACS. For those who don't know, GROMACS is a very highly optimized CPU code for molecular dynamics. It's been developed for more than 20 years, I think, has millions of lines of C++ code. And on a single CPU core on exactly the same parameter set, we are faster than GROMACS, and that also translates to dollars per microsecond of simulation. So this may not seem impressive in the first two columns, but imagine you're beating Michael Phelps in swimming. So that's the sort of analogy I would bring here. But on top of that, we have implemented state-of-the-art integrators that aren't present in GROMACS, for example. And these allow us to increase the time step to, for example, from 2 femtoseconds, typically used to, say, up to 10, which gives us extra performance. And then we also have some package to optimize parameters but while keeping the accuracy. So we can actually get to much less dollar value per microsecond of simulation. I can also present some comparison to OpenMM, which is typically a GPU, code base. But the comparison, it's hard to always pick exact parameters that will fit. So we do our best here. So to compare, as I said earlier, typically you want to run many different simulations. So in this case, we run 12 simulations on 8 cores each, and per microsecond of simulation, BioSim will be about 5 times cheaper than a GPU code that OpenMM runs. And also keep in mind that, as I said earlier, you want to run many smaller simulations, and CPUs generally are more available than GPUs. So we believe this is the way to move forward. So that's all from me. Please do get in touch for access to the platform. You can have an access like the Jupyter notebook you just saw. And yeah, if you have any questions, I'm around, and also you can email me later as well. Thank you.